Good morning, friends. I welcome you all here for my course, Engineering Thermodynamics. Course code is AAEC02 and Module 2. I have completed my Module 1, and as you know, my name is Dr. Dwivedi, Professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. Today, my topic will be second law of thermodynamics, and we have seen that following topics I have covered in my module 1, that is concept of thermodynamics, systems and surrounding, properties of substances, zeroth law of thermodynamics, thermometry, first law of thermodynamics. So in our concept of thermodynamics, we have defined that what is the thermodynamic. The thermodynamics came from the two Greek words, that is thermi and the dynamics. Thermi means heat and dynamic means power. So the thermodynamics we can define in such a way that the branch of science which deals with heat and the work with their transformation from one form to another form. So here we study about the energy. This energy may be in the form of heat or it may be the form of work. This we have defined, and we have seen the different types of thermodynamic courses like our conventional thermodynamics, then statistical thermodynamics, biological thermodynamics, chemical thermodynamics, atmospheric thermodynamics, oceanographic thermodynamics, and so on. So here we will be only handling in this course only the conventional thermodynamics. Next, we have seen the systems and the surrounding. Here if you see here, this is one, and inside there is a system here. This is the system. This is here the boundary, and here is this is the surrounding. This is the surrounding. So we have here control mass system and the control volume system. In the control mass system, the mass inside this system will not cross this boundary. That is the control mass. If you see about the control volume system, in this, mass may be in, mass may be out, and in the control mass only energy will transfer. But in this control volume system, mass and energy both will transfer. So that is the control mass and the control volume system. And we have also done about systems and the surrounding. And when you combine systems and the surrounding together, it becomes the universe. Now, if you see about the properties of the substances, so we have seen the different types of substances, and we have seen the properties like pressure, temperature, specific value. These are the properties. We have the different types of substances like simple compressible substances, ideal gases, monoatomic, diatomic, and polyatomic substances. Then we have seen the zeroth law of thermodynamics. In zeroth law of thermodynamics, we have seen that if system A is attached with a diathermic wall with the system C. This is the system C. And there is a system B, which is here is adiabatic wall. They are not, B cannot transfer the heat, but A can transfer heat to the C, and this C can also transfer to the B, or B can also transfer to the C. So as per the zeroth law of thermodynamics, if A is transferring to the C, B is also connected with the C, so A and B will also be in the equilibrium. So this we have done with the zeroth law of the thermodynamics, and we have given some examples of this, and this zeroth law was used for measuring the temperature of different substances or different systems. So thermometry also we have done in that different types of thermometer. We know that PV is equal to MRT. So if you know P, if you know the V, we can find out the T. The same way, if we can keep the pressure constant, volume vary, we can, or vice versa, we can find out the temperature by the help of equilibrium. We can measure by help of the zeroth law of the thermodynamics. Then we have seen the first law of thermodynamics for a cyclic process. The first law says that cycle integration of heat is equal to cyclic integration of work. That is for the cyclic process, and for the any process, that is del Q is equal to del E, dE, not dE plus cyclic integration, this is equal to del W. It is not cyclic. Okay, so this heat given can be converted to the internal energy or energy plus the work done. So that is the concept of our first law of thermodynamics. Now I will go for the second law of thermodynamics. In second law of thermodynamics, I will be covering the first limitation of first law of thermodynamics, thermal reservoir, heat source and heat sink. I will give a simple definition of the heat engine and the heat pump, and efficiency of the heat engine and COP of the heat pump, coefficient of performance of the pump. This I will be dealing today. So in module 2, we have the syllabus that is belongs to the second law of thermodynamics. First is the limitation of the first law, thermal reservoir, heat engine, heat pump, parameter of performance. Up to here I will be covering today. Then the next class I will go for the second law of the thermodynamics, Kelvin and the Kelvin-Planck and the Clausius statement and their equivalence. This I will be taking in my next classes. Then corollaries and the PMM of the second kind I will be taking. Like this I will be going for the next topics, and I will go with the Maxwell relations and third law of thermodynamics. This will be covered in the second law of thermodynamics, the module 2. Now I will go for the limitation of the first law of thermodynamics. The first law of thermodynamics states that when a given amount of heat is applied to a system capable of performing external work, the quantity of heat absorbed equal the sum of the increase in internal energy of the system due to a rise in temperature and the amount of external work performed during the expansion. So this we can see here that what is the statement of the first law of thermodynamics. This is our system, and here I am putting this as a system. I am giving some heat Q. As and when I give this heat, some work will be produced. So this work, or if I write del Q and del W, work will be produced. So here the quantity of heat which is supplied, it is absorbed by the system. This is the system and this is the surrounding. The surrounding is giving some heat to the system, and if you give the heat, it will start expanding. There will be change in the volume of this system, and you know that work is equal to P dV. If the volume is increased, so there will be a work, and this work will be the positive because it is expanding. If there is an expansion of the gases, work is positive because volume of the system is increasing from initial to the final. The increase of the volume is there. So this dV will be the positive. So work will be the positive. So if you supply the heat to any of the system, and this system will expand, due to this expansion of the system, a work will be performed, and this work is useful for the application any of the system. But in fact, it is not telling that how much heat can be converted to how much work it will be generated. It is not telling anything. The second law gives the idea about the direction and how much percentage of heat can be converted to the work. This also says that if you give the work, if you supply the work, the heat will be generated and some heat will be going out. Both direction it is possible. That is the one of the limitation which did not happen in the real scene. So example of the first law of thermodynamics, that is human body is subjected to the laws of thermodynamics. If I am here in this room, this is AC room. So some heat from outside cool is going to me and I am feeling very comfortable. If AC is not there, and in the summer in Hyderabad, you will see that I am getting sweat because the room is very small and it is very much closed, no ventilation and all. So I will get heat. And if in this room I am alone, and if there are some 20 people in this room, I will get more heat because the heat is given by all the people, and it is assumed it is a adiabatic room, or there is no heat transfer is taking place from this room. All heat will be accumulated. So in a room with a lot of people, we start to sweat and feel heated more if room is small. Like this room, it may be the 15 by 12, okay, like this. This occurs because our body is attempting to cool itself. Our body is trying to cool itself, so it is releasing the energy. The first law of thermodynamics entails this situation. So the first law is very much applicable for this, because the outside temperature is lesser than the inside temperature. My heat will go to the room. And like this, there are 20 people, all will try to release their heat and the room will be heated. And this will be very discomfortable. That's why we use the AC. The air conditioner will take the heat and it will release from outside. I will be discussing in this after a few slides about the refrigeration and heat conditioner, also heat engine. There I will be discussing in detail about the first law of thermodynamics. So first law of thermodynamics, it is an isolated systems. In an isolated system, total energy is constant. So that is your first law of thermodynamics, that total energy is constant. Next point, energy has the ability to transition from one form to another, but it cannot be created or destroyed in any way. This total energy is constant, means it is a conservation of energy. The meaning of the conservation of energy is that the energy has the ability to transition from one form of to the another form, but it cannot be created or it cannot be destroyed. Anyway, some of the heat supplied to the system it utilizes to change the internal energy. So here I have given here, while the remainder is employed by the system to perform work. So I am just writing a system. This is the surrounding. You are giving the energy Q, some work will be performed, and there is some change in internal energy. You can assume that this is like a bank. You are depositing some 100 rupees. You are taking out 100 rupees after 6 months. With the 6% of interest, rupees 3 will be accumulated here. This rupees 3, you can say this is the internal energy which is inside the bank, inside the system. This system is a bank. This is the system, and this you can say as a bank. You are depositor, and someone has taken, or you can also take it. And so like this, we can say that this delta U is rupees 3, delta Q is rupees 100, and delta W is also rupees 100. Or if you take some 90 rupees, then here you will have 13 rupees. So like this you can get. So this internal energy is generated by the system itself. So like this we can assume that this is the first law of thermodynamics. Now I will talk about limitation to the first law of thermodynamics. So we have done this thing, but we can observe that total heat which you are giving is not converted to the work, or if you give some work, is it able to transform to the same heat? If you see, this is a cup here. It is full of tea, with hot tea is here, and if you are, this is the surrounding here, it will emit the heat to the surrounding. Heat is emitted to the surrounding. Surrounding is here disturbed. But can we make this heat which is released, and this, can we make this tea again hot? It is not possible. So first law of thermodynamics do not give the direction, in which direction flow of heat will be there, and in which direction the flow of work will be there. This is not described by the first law of thermodynamics. So the first law of thermodynamics does not specify the direction. Just now I told. Direction, one direction is known, but another we don't know which direction it will flow. Heat is traveling through the space, which is a significant limitation. So I have given the example of this hot tea. Heat can go the surrounding, but can the surrounding can give the heat to this tea? Can this, after release of this heat, your tea is cool now, can you make hot from the surrounding without giving anything? It is not possible. So no distinction between spontaneous process or non-spontaneous process. It doesn't give anything about spontaneous and the non-spontaneous. So here initial, the heat of the tea is going to the surrounding. It is spontaneous. But what happened from surrounding to this? It is non-spontaneous. It may not give. Normally we don't see it is happening like that. So it is a non-spontaneous. Going backward in time is not a practical option. It is like can you go backward in your past? Not possible. Same way is here. Philosophical way, we cannot go to our previous time. The time which is past, we cannot go. So this is also the limitation of your first law of thermodynamics. In real world practice, the heat does not completely convert to the work. If you see if you give the 100 joule, we will not get 100 joule of work. There will be some transformation in other form. In the event that it had been possible to convert all of the heat into work, human would have been able to move ship across the ocean by extracting heat from the water of the ocean. You can see that if it is possible that like this tea, once we are releasing the heat from the tea and it is going from tea to this surrounding, if it is possible that this surrounding will also give the heat to the tea and again it will be hot, then it is very nice. We can do this continuous process and our no energy will be wasted. Here also, if you see, if you want to move a ship across the ocean, ship is giving some power or some engines are there and it is moving on the ocean, and can we get that energy from the ocean? And if we are able to extract the energy from that ocean and we can use in an engine same way, so we can go without expending any fuel, diesel, petrol or any batteries we are not required. That limitations are there in the first law of thermodynamics. First law of thermodynamics do not say about which direction the flow of energy, flow of the work will be there. So these are the limitations. Further, I will talk about the one more concept about the thermal reservoir. A thermal reservoir or thermal energy reservoir or thermal bath. Anything you can say, thermal reservoir, thermal energy reservoir or a thermal bath. Thermal reservoir is a thermodynamic system with a heat capacity so large. Like your ocean, you have lot amount of water. If you take one glass of water, nothing will happen to the ocean. Same way, in the solar energy, we put our solar panel, but nothing will happen to the surrounding temperature. It will remain the same. Like this huge amount of energy source, if you take some part of that energy, nothing will happen to that. So, thermal reservoir is a thermodynamic system with a heat capacity of huge amount, infinite amount of heat is available. That the temperature of the reservoir changes relatively little. Means if it is in the, I gave you the example. If you take the one bucket of water from a river, Ganga, nothing will happen to the river Ganga. That one bucket is infinite small, very, very, very small. When a much more significant amount of heat is added or extracted, it functions as an infinite pool of thermal energy at a given constant temperature. So, the reservoir is having a huge amount of energy, and if you take some amount, nothing will happen. The temperature will remain constant. It will not take. Example, I am here. Lakes, oceans and the rivers often serve as a thermal reservoir in geophysical processes. Number 2, in atmospheric science, large air masses in the atmosphere often function as a thermal reservoir. This is a reference I have taken from this reference. This part. Thermal reservoir, heat source and the sink. Further, a thermal reservoir is the part of environment which can exchange heat energy with the system. So, thermal energy is a very big source of energy from where you can continuously take the energy, and in reservoir nothing will change. It will remain constant. All the parameters of the reservoir will approximately remain constant. It has sufficient large capacity and its temperature is not affected by the quantity of heat transferred to or from it. So either you release in the reservoir energy, nothing will happen, or you take some energy, nothing will happen. All the temperature, all the heat content of that reservoir will remain constant. The temperature of heat reservoir remain constant. The changes that do take place in the thermal reservoir as heat enters or leaves are so slow and so small that processes within it are quasi-static. It is very, very slow. So if you take anything in a slow process, nothing will happen. All the parameters, thermodynamic characteristics will remain same. The reservoir at high temperature which supplies heat to the system is called the heat source. So the big reservoir which is giving heat to the system is also called the heat source. So what is the heat source? Heat source is a thermal reservoir which supplies heat to the system. For example, boiler furnace, combustion chamber in an engine, or your turbo engines or the IC engine, nuclear reactor in a nuclear power plant, they are the thermal reservoir. They generate huge amount of energy from the system. The reservoir at low temperature which receives heat from the system is called the heat sink. So heat source which supply the heat to the system, and the heat sink is the reservoir which receive heat from the system, and this is at the low temperature, lowest temperature than the whole system. For example, atmospheric air, ocean and the river, they can be used as a heat sink. So here I am depicting this source and the sink. Depiction of the thermodynamic source and the sink. So this you can see here that this is the source. This source having huge amount of having huge amount of the heat, and some amount of the heat is extracted, that is called the Q in. This goes to a working, it may be engine or it is going here, and due to this heat, this engine is supplying some work. This is work out, and the remaining work has to go to the sink. This TC is very, very less than the TH. TH means high temperature and TC means it is a cool temperature, and this is called the sink. Where heat is released, that is called the sink, and from where heat is taken, that is called the source. Source will be a huge amount of energy. So energy, it is containing huge amount of energy. If you take some part of the energy, the parameters or the temperature will not change. Same way, in the sink also, it is also a very low temperature, but whatever energy you release in this sink will not change its temperature. It will remain the same. So heat source will also not change its thermodynamic property, and the heat sink also will not change its thermodynamic property. Now I will talk about heat engine. So, because to understand the heat engine, we should first understand the heat source and the heat sink. We have already just now I have described what is the heat source and what is the heat sink. So now, what is the heat engine? Heat engine is a system that converts heat to the mechanical energy, which can then be used for the mechanical work. So the heat engine is the device which converts heat into the mechanical work. It does this by bringing a working substance from a higher state of the temperature to a lower state of the temperature. So what is the purpose of the heat engine? It takes the working substance from a high temperature, that is the source, and it releases this temperature to a sink, that is in the lower state of the temperature. A heat source generates thermal energy that brings the working substance to the higher temperature state. So the heat source is the very big amount of heat is available that brings the substance to a higher temperature. The initial state of the temperature should be high, then only engine will start working. The working substance generates work in the working body of the engine while transferring heat to the colder body is called the sink until it reaches a lower temperature state. So from the high temperature, the source, the heat is absorbed on the engine, and from some part of the heat is released to the sink, which is colder than the whole system. During this process, some of the thermal energy is converted into work by exploiting the properties of the working substance. So there is a source, there is a sink, and there is a device. This will work out, and here is the QL and this is the QH. So this Q is, and this is called the engine. Heat engine. So in this way your heat engine is working. So during this process, some of the thermal energy is converted to the work by exploiting the properties of the working substances. The working substances can be any system with a non-zero heat capacity. The working substance, the heat should be non-zero. Some heat should be there, but it is usually a gas or the liquid. Normally, it can be anything, but normally we use the gas and the liquid because we cannot use the solid for expansion and all. It is somewhat difficult task. During this process, some heat is normally lost to the surrounding and is not converted to the work. So in this, some heat energy is lost in the surrounding, and so 100% is not produced. The work is not produced the 100%. Also, some energy is unusable because of friction and the drag on the system. So these are the some concept of the heat engine and how the heat engine is working. This we can see here, the heat engine efficiency. We know that the heat engine, we call it as efficiency, means just now in the previous I have that during the process some heat is normally lost, not converted to the work, and also here due to this total heat is not converted to the work. So how much is converted? Means output, work output divided by the total energy supply, which we tell as a efficiency of the system. So here we have the hot source, that is TH. This is extracting heat, QH. This QH is going to the heat engine. This is called the heat engine. This heat engine is converting this. It is receiving a hot gases from here and it is converting to the work here, W, and some part is released in a cold sink where temperature is much lower than the engine. So it is called the QL. So what is the efficiency? efficiency of the heat pump, it is eta. This eta is equal to work out by heat given, So what do you need? So what is the meaning of efficiency? What you need divided by what you pay for, or output divided by input. So what is the output? Output is QH minus QL. And what is the input? Input is QH. So here we will get 1 minus QL by QH. So efficiency, we can tell that efficiency is equal to 1 minus QL by QH. So always this number will be always some positive number. QL by QH means the ratio of heat released to the ratio of heat extracted. How much this number? So always neta will be always less than 1 or less than 100%. That is the limitation of the first law of thermodynamics. We can't get the energy what you supply, that much amount of work you cannot get. There will be some losses. So the efficiency of any engine will be always less than 100%, maybe 70%, 80%, 90%, but it is always less than 100%. That is the heat engine and their efficiency. I think it is very much clear. So now I will go for the next topic, that is heat pump and the coefficient of performance. COP is what? Coefficient of the performance. Here it is very much essential to mention that for the heat pump and for refrigerator, we don't use the efficiency. We use its coefficient of performance, because we have seen that the efficiency always will be less than 1, but COP will be always more than 1. So that is the specialty. So we don't say it as a efficiency. So because coefficient of performance will be always more than 1. So definition of heat pump. A heat pump is basically a heat engine run in the reverse direction. So what happens in the engine? We take the heat from the source and we operate a machine that will generate the work, and some heat is released. But in heat pump, what happens, especially in cold countries and all, our room should be hot and outside is very much cold. So we take that heat from the cold, we give some work and we release the heat inside the room. So your room is hot. Same way in the refrigerator which we use in our home, inside the temperature is, we want to make the cool. The inside temperature may be 0 degree or minus 2 degree or 2, 3, 4 degree inside. If it is freezer, you will get minus 4 degree, and so that much we have to maintain inside your refrigerator. So in that case, we have to extract the heat from the refrigerator and we have to supply. Your air conditioner, we want to maintain the low temperature inside the room and outside temperature is high. We are extracting from low temperature and we are supplying to the high temperature. It is not possible. So we have to give some work. So the heat pumps and the refrigerator, they are used for this purpose, for cooling of the ambient where we stay. So a heat pump is basically a heat engine run in the reverse direction. In other words, a heat pump is a device that is used to transfer heat energy to a thermal reservoir. So from a sink to the source, we are supplying. From low temperature zone to the high temperature zone. From low to high, we are going and we are giving it is not possible by a normal way. We need some additional work to be done. And that device which is doing this work is called the heat pump or the refrigerator or the air conditioner. In other words, a heat pump is a device that is used to transfer heat energy to a thermal reservoir. They are often used to transfer thermal energy by absorbing heat from a cold space and releasing it to a warmer one. I told you that in a cold weather condition, outside is cold and inside is hot. We want to make inside also cool. So we have to take this hot air from the room to outside, which is already cool. It is not possible. So we need to do some work. They are often used to transfer heat energy by absorbing heat from a cold space and releasing to the warmer one. So this is, you can see here the diagram. This is your room. This is your room here. Assume that the room you want to maintain 15 degree centigrade, and this is the outside temperature. In India, Hyderabad, it is 40 degrees centigrade. Assume we want to make this 15 degrees centigrade, but here outside is 40 degrees centigrade surrounding. So what I have to do? I have to fit a heat engine. This heat engine will operate by the help of electric motor or some IC engine. It will operate. We have to give some work here, and it will extract this energy from here, and it will maintain 15 degrees centigrade, and it will release to the 40 degrees centigrade. So QH is equal to QL plus this work done. Here QL plus, so QH is equal to QL plus work done. This is the process here. So we can write the coefficient of the performance is equal to ratio of the desired effect with work input. Ratio of the desired effect divided by work input. We are giving the work, so it will be divided by the work. So COP is equal to desired effect divided by required input. So here the required effect is what? QL. We want to maintain QL divided by work in, and this we can write that COP of the heat engine is equal to QH divided by W in. So this is for the refrigerator QL by W in, and for the heat engine it is QH by W in, and this QH is equal to QL plus W in divided by W in. So 1 plus QL by W in. So this is always positive number. So COP will be always greater than 1. This is the which we have got the concept. Relation of coefficient of pressures of heat engine and the refrigerator. This I am going to discuss here, that what is the difference between heat engine and the refrigerator. Refrigerator is the device which extracts the heat from a cold source and it is releases to the outside. But the objective of heat pump is to take the heat from the cold atmosphere and make your room heater. That is the difference. So COP of the refrigerator, assuming that heat engine and the refrigerators are working in the same temperature range, that is TH and TL. Both are working in the same zone. So COP of the heat pump minus. So we can see that heat pump WL, no, so QH minus QL is equal to W in. QH minus QL is equal to W in. So COP of HP minus COP of the refrigerator is equal to QH minus QL by W in. So COP of heat pump minus COP of the refrigerator is equal to W in by W in. So this cancel. So COP of heat pump minus COP of refrigerator is equal to 1, or COP of heat pump is equal to 1 plus COP of refrigerator. So whatever you are getting the COP of the refrigerator, the COP of the heat pump will be, you add it 1, you will get the COP of heat pump. So the relation between COP and the COP of the heat pump and the COP of the refrigerator is add 1 on the COP of the refrigerator, you will get the COP of the heat pump. Thus, this shows that COP will always be greater than 1. So, the name given as coefficient of the performance, not the efficiency, as the efficiency is always less than 1. So, we are given COP, not efficiency, because COP is always greater than 1. So, that is the concept of COP and the efficiency of engine. Performance parameter of thermodynamics. The central concept of the thermodynamics is that of energy, the ability to do the work. It may be transferred into a body by heating, compression, or addition of matter and extraction from a body, either by cooling, expansion, or extraction of the matter. For comparison in mechanics, energy transfer results from a source which causes the displacement. The product of the two being the amount of energy transferred. In a similar way, thermodynamic system can be thought of as a transferring energy as the result of a generalized force causing a generalized displacement. So force into displacement, F dx, is the energy. These thermodynamics force displacement pairs are known as a conjugate variable. They are force and displacement, they are called the conjugate variables. The most common conjugate thermodynamic variables are pressure volume, that is the mechanical parameters, temperature and entropy, they are the thermal parameters, and the chemical potential particle numbers, they are the material parameters. So we have mechanical parameters, thermal parameters, and the material parameters. Next topics, I am going to discuss about the second law of thermodynamics in detail, Kelvin and the Planck statement, and then I will go for the Clausius statement. For my next lecture, it will be totally dedicated for the second law of thermodynamics. These are the references: P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's 4th edition; Eunice Sengel, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition, 2011, and I have taken this from the Wikipedia about heat engine. Any questions, you are welcome to ask. My email ID is here. Email ID dwivedi@gmail.com. Also, I request you to like and subscribe this channel. It will give me very pleasant atmosphere and it will enhance my morale. If anywhere you feel that I have done some mistake, let me know. I will try to correct it. Thank you very much for the joining. Be tuned for my next lecture. This will be very interesting for the second law of thermodynamics, and it will be a very good exposure. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.